extrapolate that the corresponding solutions down here are on the x-axis. All right? Yep.
How did you end up with that green line? Like,
I said consider this energy. They're given to you in the problem. I say energy E1, E2, E3, E4, E5, E6. Analyze blah, blah, blah.
okay.
So I gave you, to simplify my life, I gave you energy levels to look at.
Okay.
If I'm adventurous, I'll tell students to pick a few energy levels and make an interesting graph, but that turns out not as well. But it would be somewhat analogous to asking the question, like, where do you start graphing? You know, I mean, you have to pick an energy level. But once I do that, then this gives me curves like this, going from here to here, something like and then over here, another one of these guys. If I'm doing this right, I should hit horizontal tangents, the critical lines, right? The critical points up here are, they're v equals 0 on those lines. Not v equals 0, how to say this? dv dt is 0 over the critical points for the potential, which means that the graph has horizontal tangents over this. I should have horizontal tangents here, horizontal tangents there, horizontal tangents here if I'm doing it right. So like, if I did this right, I should hit a horizontal tangent here and here, if that makes sense. My picture is not always that awesome, but that's what I aim for. Right? So another interesting question is, given energy E1, what are possible motions? I can tell you possible motions are only given to the left of that hump there, between, in this valley right here, between these two x values, or to the right of that. I cannot have motion in the dotted regions, if that's my energy level, classically. In quantum mechanics, it's possible. In fact, this is the foundation of most of semiconductor technology, is tunneling. Another energy level we should look at. Let me see if I got a better color. I got an orange. You know, I used to have pink. I don't know what happened to my pink. Oh well. So just, you'll have to use your, I'll make one of the energy squiggly or something. So I think I can do a blue one. This is an interesting energy level, the one that is like this. So let's call that E2. Again, this is forbidden, classically. Right? So E2 is interesting. That actually corresponds to the solutions that flow through. Let's see here. So we get velocity 0 right there. No motion between here and here. Some kind of fishy thing going on here. Something like that. I didn't do it quite justice. Again, I should really aim for like horizontal tangents as it hits the critical line here. I tried. I mean, this is a somewhat qualitative method I'm telling you here. So there's the energy level E2. I can tell you what direction the motion goes. That's easy. Like so, like so, like so, like so. Always left, below, and right above. Another. Let's see here. Let's do E2 up here. I'm trying to make it hit the, just hit the top of that one. I mean E3, sorry. That was supposed to be straight. So here, no motion's forbidden. Energy is greater than the potential energy everywhere. So there's no forbidden region. But it has velocity 0 right there, apparently. All right. And I got to be careful. I should still hit like horizontal tangents as I cross through. I have to think about this. Something like that. So I believe this would be something along the lines of and it should be symmetric. Up to the limits of my artistry. There you go. That's there you go. That's the E2 curve. Right. And then if you get energies above that, then that would look something like I can't. I've not made myself a good. So I don't do as well for these. It's my bad. They should have horizontal tangents like here, and also here. There should be horizontal tangents, and then they generally are reflective. I mean, the general principle is what that. Well, I just failed altogether there. Let's see here. I really have trouble graphing down here. Well, I'm just going to put a big old quotes around this one. Just know that that's wrong. So general principle is the energy is conserved, right? So when if your energy level is way above the further it is above the potential energy, the faster you're going, which means that you're further up in the graph, right? So like the distance. This distance should also be reflected in some sense in how far this is bending up relative to where it was. Let me do another. Any questions? Oh, yeah.
So the E values that you pick, would they represent like the total energy in the system?
Yes. Right. So for example, for this one, if I had energy level E5, then it's very boring. It's just the only thing here is like this. There's no motion possible over here because everywhere over here, your energy level is less than the potential energy. Here's one you guys are more familiar with physics. I've given you a complicated example, now I'll give you an easy one. This, of course, is the potential energy, like 1/2 kx squared, right? Potential energy from a spring, right? So you've got what? You just have your one critical point, 0. And so if we draw the so-called Poincare plot, which is down here. Then let's see here. I could draw energy levels. Of course, where you set the 0 is not written in stone. And but once you choose it, you chose it, I suppose. That so like here, if this is my energy level, wherever my energy level, say E1, intersects the potential energy, that means I've got 0 speed, right? So 0 velocity here. And then I have to have horizontal tangents, which means I have my maximum Where I have the minimum potential energy, I have the maximum kinetic energy, right? So that's like these 2 points. Something like that. And then if you go up a little bit more, say E2, that would look something like this. Up to the limit of my artistry, these should be horizontal tangents, right? And if I went up further, well, that gives me something like this. So this is a picture which illustrates the possible motions of a spring. You know, we talked to you guys about those 4, like sort of 4 regions of motion: stretching, compression, you know. Right? If you, in your physics book, there's this picture of 4 different regions of a spring motion, right? It's going up, it's stretching out, or it's up and it's coming back, so it's compressing, but it's still for positive. It's above the, you know, the equilibrium point. Then it's below the equilibrium point going down, and so it's compressing for negative. And then it reaches its maximum compression down, and then it goes back up again, right? And then there's these 4 different cases. Those 4 different cases are all pictured here, right? Like here you have velocity, rightward motion, and it's stretching out. This is its maximum extent for that given red energy level. And then it pulls it back, eventually gets to the largest speed through the equilibrium point going to the left. Then it compresses, gets to its maximum compression, then bounces back, speeds up through the equilibrium point going to the right. You can see all of that in this picture if you just start looking at it. It's all there. Right. So to give you an energy, an impossible energy here, you know, if I give you energy level less than 0, well then there's no motion possible, right? So I think I have maybe an example. I think if you look at old tests, I might have 1 or 2 of these somewhere, but I hope that's enough to get you started. I think that the challenging problem is the one where you have to, I mean, to me, given this, getting that, it's pretty routine, right? But to me, what's much trickier is the problem I gave you, where I gave you a picture and said reconstruct the potential. But that's actually kind of one of the interesting things to think about is maybe you could take data and, you know, look at possible velocities and positions, and from that you can extrapolate what the energy of your system was. I don't know. Maybe that's possible, maybe it's not. Hopefully you can do the homework question. I don't think it's too complicated. So. Well, have a good weekend. I guess you have some work to do.